100 degrees centigrade. So you need ductility at low temperature, because surgeon can just say, oh, no, I need to do something here. I need to change it. So there's a lot of requirements in this particular design for deformation. You need to start with something that has a very good homogeneous thickness if you're going to deform it. Otherwise, you'll form necks. And it's under pressure, so you also have to be very careful in not having areas that are thinner than others. And when you're dealing with this type of wall thickness, it's difficult. You can't drill this. You may be able to drill it over a short period of land, and that's what we're working on for some of the prototyping work. But ultimately, you need to use these processes here, extrusion, drawing, to control the wall thickness. And it becomes important. In this case, we want something that's a low strain. So we do want to be at a certain temperature when we finish. So when we cool it down, it's a relatively low yield strain. Otherwise, we have to go and do annealing after the fact. So I'll pass it around. So this is injecting the liquid from here, and between the tube you have your exhaust coming back up. And that goes to this one. So that's a manifold here that separates the liquid from the... and there is a way where you reverse the flow just a little bit, and you heat it back up very quickly, so you can take it away and not touch any other tissues. So this needs to be able to cool down and reheat. Essentially, it's the base concept. And you can see that there are a lot of possibility for optimization. Surgeons want to be able to bend it themselves. They don't like using tools, but then it's very hard to make the material good enough so they don't risk of forming a kink. And in this particular layout you have here, you can see the inner tube is actually going to help preventing the kinks, because it's taking up space. So it will only go oval to a certain point during deformation. So it's an example here where we use, for this project, we have to get our billets done, and then we have to get them worked to a smaller bar, and then either machine it, extrude it, deep drawing it. And people our client is very interested. They have this very particular need of low strain. It's very unusual. And what we find, however, it's hard to get locally, nationally, equipment to run experiments, because a lot of this deformation processing work is done overseas now. So if we go to Germany, it'd be a lot easier to get this very advanced technology to make the very, very fine extrusions. So it's just the way it is. But it's good for us to understand it. Don't get me wrong with that. I think that it's key to be able to understand, well, first of all, what's the difference between hot roll and cold roll? Right? And that's one was a question. I worked in a factory once, and they said, oh, you're a material guy. Oh, yeah, well, so why do we have all of this? Okay, now we're getting into what happens when you deform. I think you'll find it interesting. We're not going to address specifically dislocations right now. We're going to do that a little bit at the beginning of the next class. So before I move to that, any question about kind of like the processes of that deformation? Because I sort of moved around. I talked more about rolling than anything else. But all these forming processes, there's a full module on that webpage Professor Eager showed yesterday. It's a full 12 hours on the different ones, the forging, what matters, how much deformation you can get. So there'll just a lot more details than what I could give to you guys. But if there's any question, I'd be happy to entertain here. You guys want to? Yes?
How do you actually make a very thin walled tube? I mean, what do they start with?
About 3-inch diameter is the smallest stock that a commercial extruding machine will take. For us, it's a problem, because we don't need a whole lot of material here. But we need to get these billets that are 3-inch in diameter, at least a foot long. It's the smallest they'll take, because by the time that the process becomes controlled, you've already done probably 500 feet of tubing. I mean, no, I'm exaggerating, but it takes a while for the process to stabilize. And part of our job is to also try to vary the processing temperature to get different level of ductility and initial yield strength. It's a good question. Thank you.
But how do they make the hollow? If you start with a solid.
So you need a die essentially in which it will just go through. It's you can if you process meat, you kind of do the same thing. You just work everything through a die, and there's only so much you can get through it. So you're not making it continuous at that point, but you get to a maximum depth of it. The other way to do it is by drawing. Drawing will get you a better tolerance, but you're limited in terms of the length you can do, and it's mostly to control it's better at controlling the outer diameter than the wall thickness. So we've been like going through a bunch of iteration about how to get the better wall thickness tolerance. The best we can get right now, we think, is 2 mils, plus or minus 1 or 2 mils, for a wall thickness of 25 mils. And they, in their initial prototype, were not anywhere close to that. They had at least 25% wall thickness variation around the circumference. So it is an improvement, and it's something that needs to be, we need to keep working on it to get what we want. In terms of what happens in the material during the deformation, I put it here as recovery. The recovery just means you have a positive dislocation and negative dislocation. They combine, it's gone. That's really what I want you to remember about that. The recrystallization, that's a little bit more complicated. What happened here is the grain gets filled up with so many dislocations that it's easier to take a little corner between the grains and just make a new grain. So there's a small grain that has low dislocation that's going to initiate, and that's our nucleation discussion from the casting. And that one is so much less energy that it will eat out the deformed grains. It's probably a good way to think of it when we say recrystallized in this context. The recrystallized grain are not any bigger because they really just come and try to eat out the others. There's a time involved in growing the recrystallized grain that make it such that a lot of them will start to form at the same time, and you don't get a lot of variation in grain size through recrystallization. It's a good way to make sure, essentially, when you have recrystallization, you ensuring that you have a fine microstructure. The grain growth is where the danger comes in, and for that particular example here, dealing with almost pure aluminum, it's very hard to deal with grain growth. In grain growth, you're just trying to reduce the total area of interface between grain. And when a grain becomes bigger, it's more efficient at eating away the other grains. So that's what we call anonymous grain growth, where you can have big grains with small grains at the same time in your microstructure, and that's a big problem in terms of deformation processing and service as well. So whenever you think about grain growth, it's probably in all of this, it's the area where you have a consequential risk for processing and usage. And you try to minimize it, but it's very delicate because all these processes, this is essentially the temperature going up. And when I say recovery first, it doesn't mean that you don't have recovery when you recrystallize, but it's just you get to activate larger scale phenomena in your material. So I want you to keep it in mind in that perspective. Dislocations are always going to be there. At cold temperature, you don't have as much recovery, At the same time, you can't recrystallize, so it just builds up. And you come to this very saturated microstructure, and that's what we're seeing here. These elongated grains that we find in aluminum alloys, for example. When you heat up this material, you see your ductility going up and your strength going down. It's very much of a compromise. Most of the time, we don't really use annealed materials. We try to get some strength out of them because we still can have enough ductility in metals. This example here is a little bit of a problem, because if I go and anneal these tubes to the largest extent, it also means there'll be more hardening when I start bending them. So if I bend it in one way, and then I want to bend it the other way, it's going to be much harder. So it's a very significant disadvantage of just trying to work with these basic phenomena to get everything working for you altogether. When you increase the yield strength, it's harder to bend it on the first place, but it's going to be almost the same to bend it backward. If you use the lower strength, then you have a lot more hardening, and bringing it back is going to be a pain. So it's a very delicate compromise, and it turns out that the dispersion stuff, the other ways of hardening than by working, can help here in this situation. So I want you to keep in mind that the recovery is pretty much the only, I'll take it back. I was going to say it's the only thing that's going to happen at ambient temperature. It's not true for tin. We get tin alloy and lead to recrystallize at ambient temperature, and that's why they're so deformable. Yeah, they're going to keep deforming and deforming, and they don't mind if you go back and forth 10 times, because it's self-healing at the same time. As long as you don't put too much tension to initiate crack, you can keep deforming them at ambient temperature without increasing too much the flow stress. So that's really what I wanted to cover today. I hope you come home thinking, okay, I'm not going to make that mistake. I'm not going to think that the stress strain curve that you get out of an Instron machine or MTS is all you get out of the material. It breaks at 20%, that's it. It's because of that instability, the cone cup structure, the formation of the crack. If you're in compression, you can, at ambient temperature, get more than 100% deformation, and that's what you take to form the head on that bolt that we talked about. So the hydrostatic pressure eliminates the crack formation. You get all these processes of recovery and recrystallization that we make use. If we didn't have this, we couldn't do deformation processing, because the strength would keep going up. So that's why we work with temperature, and we work with geometry to make sure we keep it in compression, and at the same time we have these processes into the material going on to make sure we don't increase the yield strength too much. The dislocation density is just something to keep in mind, that it will have, the driving force for it is deformed grains. So if you don't have a certain amount of deformed grains and you eat up your material, it won't recrystallize. You're out of luck. So the more it's cold work, the more it has dislocation in it, the faster it's going to essentially transform into new grains. So that's really what I had for you guys today, and appreciate you all seem awake, so that's great.